enhancing programming with parts-based programming. We already have the technology to implement parts-based programming. These key concepts will be discussed in the following slides. Isolation, the concept that connections are triplets. The idea that connections link ports that define specific data entry and exit points of parts. One input queue per part, one output queue per part. Improved syntax that makes it easier to express connections between multiple input and output ports. Isolation is the concept that both data and control flow are encapsulated and scoped. Opcodes are data, but the interpretation of opcodes is not the same as data. Object-oriented style inheritance is okay for structuring data, but is not okay for structuring interpretation and sequencing. We've seen isolation before. Unix processes implement isolation. Functions and methods and CPS and blocks allow non-structured use of control flow. They only implement data encapsulation, but do not implement full isolation. When Unix was invented, the idea of closures didn't exist. Lisp 1.5 introduced anonymous functions, lambdas, but everything related to Lisp was avoided at the time. Today, it is easy to build a dispatcher function that contains a list, or a tree, of closures. A dispatcher simply invokes closures in an arbitrary order. This is what operating systems do. But operating systems were traditionally written in assembler or C. Today, we can do the same things in just about any programming language. Isolation means that data flows through well-defined ports. Control flow doesn't leak out. Instead of calling other functions directly, parts yield back to the dispatcher. In essence, parts coroutine with the dispatcher. Parts can only call functions and methods that are entirely contained within the parts themselves. Parts can't call functions in other parts. Parts can only send and receive data packets. By default, parts don't wait for answers, they just fire and forget. Software architects can synchronize parts with other parts, but this must be done explicitly. Current programming languages synchronize code in a stepwise, very low-level manner. This is unnecessary and results in hidden gotchas and debugging headaches when doing anything other than computing results without considering sequencing. With full isolation, parts are like little black boxes. You don't care how they are implemented internally. In fact, you can't care. You can't see what's going on inside. Full isolation is what gives Unix pipelines their power and flexibility. Function calls cause tight coupling and discourage flexibility. The common idea of function libraries creates systems that are rigid and non-flexible. The scaffolding needed to support the pervasive use of functions, context switching, and associated hardware, along with tightly coupled function libraries, leads to bloated software and to bloated operating systems. Parts don't terminate. Parts run once for each input event. State, if any, is persisted between runs. Events can come in at any time, one by one. When a part handles a single input event, the part might generate 0, 1, or more output events. Typically, connections are considered to be pairs, a sender and a receiver. If we add one more field, direction, then we can compose parts, like how Bash scripts compose commands, or Lisp lists compose lists out of atoms and other lists. The across direction is what we usually think of as a connection. Adding down and up directions allows us to connect inputs and outputs of container parts with parts that are inside of the containers. The through direction is added for completeness. It turns out to be useful for stubbing parts out and for signaling when container parts are ready to yield and to pass the baton on to other downstream parts. Here, I show the 4 different directions. Across goes from inner part to another inner part. Down goes from the inside down to one or more inner parts. Up goes from inner parts back up to the output of the container. Through goes from the input gate of a container directly to its own output gate. It is important to think of parts as black boxes with well-defined input ports and well-defined output ports. Wires cannot poke through the walls of black box parts. Wires can only connect ports that are on the perimeter of parts. This may seem obvious, but it helps to make this concept very explicit. It changes the way that the code inside of parts is written. For example, Functions inside a part cannot call functions outside of the part. At best, functions can send data messages out through ports. The use of functions is not prohibited, but function calling is scoped. What goes on inside a part stays inside the part, whether it be a chain of function calls, persistent state, whatever. The only thing that moves through ports is data. This is not what happens with functional programming. Typically, functions are allowed to call other functions anywhere else. This is true even with dependency injection. The call-return protocol implies blocking, and we can't have that. Only messages flow through ports, not control flow disguised as function calls. Functions are a useful concept in mathematics, but when mapped onto hardware that is constrained by reality, like the speed of light, functions don't model the operations of computers accurately unless the computers are used only as calculators. We can't avoid dealing with deadlock, but we must ensure that our tools cannot create hidden kinds of deadlock, and we must ensure that our tools give us enough flexibility to explicitly deal with the problem at an architectural level. In addition, we need to reason about messages in order of arrival. The policy of having only one queue per part is simpler than the idea of one queue per port, and allows software architects to reason about and handle these situations. We need to ensure that our tools do not introduce hidden forms of coupling, like control flow transfer caused by function call blocking. Using data queues at the front end and back end of each part isolates parts from one another. Again, a single queue allows the tool to keep messages ordered. Current line-oriented syntax, like that of Rust, Python, etc., obfuscates the idea of using multiple ports. Better syntax, like, say, using diagrams, makes multiple port compositions more obvious to the human eye. Some existing diagram editors are compatible with existing parser tools. These diagram editors save diagrams out in less human-readable textual form, but this format is machine-readable and can be easily parsed with existing text-based parsing tools like OhmJS, PEG, etc. Due to hardware and software limitations of early computers, it was common to conflate syntax with semantics. Today, though, it is straightforward to separate syntax from semantics. Tools like OhmJS can parse text, and techniques like using dictionaries and relational programming make it easier to express semantics. In fact, we have many compilers that inhale textual syntax and produce machine-executable code. JavaScript, Python, Rust, WASM compilers convert high-level languages into executable code. We only need to convert diagrams into any one of such languages. We don't need to build full compilers, since the existing language compilers can do that work for us, once diagrams are converted into high-level language text code. We even have a workable textual intermediate language, JSON. Most modern languages know how to internalize JSON or have libraries to do so. For example, we could simply convert diagrams to JSON, then use relational languages like Prolog and Minicanran to infer hoary semantic relationships within the code, then emit legal Python code and let Python do the rest of the work. We could even use loops within loops and sidestep the use of relational languages entirely.